Thank you, and thanks for the invitation. It's a wonderful event, and so unfortunately, we were not able to finish writing our paper, but having this event really pushed us, and and so hopefully we finish the first draft soon. Yeah, I mean it's actually close to being complete. And anyway, so I'll talk about this Cuspidal sheaves. So it's entirely on the spectral side. But I'll start by some observation on the geometric side to motivate something. Before I forget, later I talk about the spectral side, but my default convention is coherent sheaves are always Kaj-compact support. Okay, and also maybe everything is over QL bar. Okay, now some observation on the geometric side. So I'll take a basic point, and the representation there, so pi, of GB of f. And then I have the sheaf on G corresponding to pi. But let's say I have another point, B prime, and that's different from B, and another representation, pi prime. And also say, let's say this is non-basic. Later I vary B, so this is a representation of GB prime. And then I look at the R home, IB prime, no, sure. So this function is explained, right? It was explained. So this function is left adjoint to the pullback. So this is the first functor. So this is the pi prime right? But B prime and B are different points, so this is just 0. So this vanishes. So this is a trivial observation. And so I'm not sure geometric Eisenstein sheaves was discussed enough, but the source of this form this one is a particular, can you read? This one is a particular case of the Eisenstein series. So B prime provides some parabolic subgroup PB prime, say, and also the Levy subgroup. And then this element B prime lifts to a basic point of BM prime. I'll just use the same notation, okay? And then this one can be written as a Eisenstein series PB prime of, I guess, IB prime pi prime. Thank you. Yeah, I forgot. Yeah, so B prime is a basic point, open point, and pi prime is just supported at that point, and then take Eisenstein sheaf. And then you get this sheaf. So somehow, this condition says certain home from Eisenstein series vanishes. And you can easily generalize to, so more general statement is the following. So F is now a general sheaf. And F is supported at basic point. If and only if like this kind of R-form vanishes. So R-form I's, say G, F, and P vanishes, and G satisfies certain condition. I mean, but G has disconnected component, and G has some condition related to that. So this is like a strictly P dominant.
Where your P is PB prime for some B prime? P is just a parabolic.
Yeah.
Any parabolic?
Any parabolic, no. Right? So this is equivalent. And you can also change this a little bit. So namely, I can further, okay, so basic, F is supported at basic point means this is a sum of like IB showing pi B, and pi B is an arbitrary representation. But I can ask like pi B to be super Cuspidal. And then I can delete this strict thing. So the sheaf G, like you are applying Eisenstein series, is really P dominant. Okay? So this is something you can prove on the geometric side, and I guess maybe a reference for this is Hansen-Hammer-Schulze.
It's actually in the paper with Lucas, some sections.
Oh, okay. Anyway, and then I mean this basically suggests like corresponding notion on the spectral side. Okay, any question? All right. Oh, so the G is a sheaf on band D band M, and band M has a like connected component indexed by like yeah.
It's only supported on
Right, exactly.
weights and stuff.
Yes. Any other question? Okay. So now I move to the spectral side. So F is now an intercoherent sheaf. And we say F is, well, right basic or Cuspidal. Oops. Something wrong happened. Okay. If like similar R-form vanishes, namely like there is Eisenstein compatibility conjecture, so I just use the Eisenstein series. So R-form I spec. Maybe later I'll drop spec, but let me emphasize here. And G is strictly P dominant or dominant. I mean, arbitrary P dominant. Okay, or you can like restate this condition using constant term functors. Namely, this is equivalent to the constant term of F and chi part, which Dave talked about, vanishes for chi, which is like a P dominant or strictly P dominant. So he explains the proof of like like vanishing for most, I mean, except finitely many dominant chi, it vanishes. But here, the condition is it really vanishes. Okay? All right? So this is the main definition. And we are basically going to study this Cuspidal sheaves. And we say, I say like this right basic, right Cuspidal, because there is a kind of dual notion. So, or maybe one notation. So let me write the category by like R basic, R cusp inside in the code.
So right basic is the one with strictly predominant and cusp.
Right.
No, there's right basic and right cuspidal. Right basic you have strictly, right cuspidal you don't have strictly. Sorry, I thought.
Okay, maybe I,
Right
yeah.
versus left is like whether you from to or from an eyes.
Uh-huh.
I guess we'll see that soon. Sorry.
Also, just to remind myself, on the dominant things on the Eisenstein series, you see MBs, or you see the classifying types one. Because I get confused between dominant and anti-dominant. Which ones are MB and what?
Let me not, but like on the spectral side, it's really dominant. And forget geometric side. Yeah. Okay. But actually, it comes next. So I'll define left basic and left cuspidal using, so this is left and basic and left cuspidal using similar condition. But now this is a mapping to home into eyes. But now the condition is anti-dominant. Okay?
Is it because you kind of need to change the PT opposite property?
Well,
I mean, when you
not really opposite, but maybe one easy thing you can prove is the following. If F is coherent, and then the left cuspidal and right cuspidal, or left basic and right basic correspond under Grothendieck cell duality. So so this. And Eisenstein sheaves functor commute with Grothendieck cell duality. So you see basically the Grothendieck cell dual of G, but then the dominant weight becomes anti-dominant. Okay? Of standard, yes. Or any parabolic or, yeah. Okay, let's say standard, yeah. I mean, it depends how to formulate, but yeah. Okay, any other question? Okay, so this is easy. Then I mentioned, I believe in like not easy things. And it's a consequence of like our later theory of Cuspidal sheaves. So more difficult results. I mean, it looks pretty simple, but I think it's difficult. For instance, like L basic and right basic, they agree. Okay? And the same for cuspidal. So L cuspidal, right cuspidal, R cuspidal agree. And for coherent sheaves, this actually means like, say, like right cuspidal sheaves are stable under glutamic cell duality, right? Because like left cuspidal and right cuspidal are solved by duality. Okay. And also, so I guess my notation is like use same thing is called basic and cusp. Okay. And these are compactly generated by coherent basic sheaves and coherent cuspidal sheaves. So, what else? So earlier I mentioned like where? Yeah, at the beginning. Yeah, I explained like this kind of sheaf is Eisenstein sheaf. So it's really basically describing the sheaf supported at this given point B prime, right? And if you think about like, I guess this was already explained, but like on the geometric side, you have a semi-orthogonal decomposition using sheaves supported at each point, right? And there is a corresponding semi-orthogonal decomposition on the spectral side. So, namely, for each B, I'll consider something like a Eisenstein series, I mean the spectral one. And basic sheaves on MB, and whose weight is correct. So I guess whose weight is like B. Right? I mean, after applying Eisenstein sheaf function, it should have correct point in the correct position. So say on the geometric side. Yeah. Okay. So I can consider this kind of categories. And then this is a semi-orthogonal decomposition. Okay.
Sorry, could you say again what is the superscript B?
Oh, this is a weight. Weight. It's a central weight. So sheaf in the intercoherent sheaf on this like Paru MB has a decomposition along the central character, and that B is really that weight.
You can think of B as living in B of NB, right?
Yeah.
It's basic there.
Right. Yeah. Okay. Any other question? Are you happy with? And also you can describe the like basic sheaves using cuspidal sheaves. And also there is a version of, namely like, for representation category, you have this Bernstein decomposition using supercuspidal support. And so you can like get a like final version of this semi-orthogonal decomposition using cuspidal sheaves. So there is a version. Using certain like ice cusp. But I omit the precise thing. Okay. Okay. So these are kind of like natural things that you want to expect based on the geometric side, but it seems actually difficult to prove. But we actually start by analyzing like really, or start by classifying cuspidal sheaves, and that's actually like possible. So the second talk, I guess, basically the rest of this talk and the second talk basically discuss the classification of cuspidal sheaves. Okay, and so this involves many reductions. And like analogous things, I mean, like Cuspidal sheaves, something like in several different settings. So I just give overview of the, such things, okay? So let me take parameter, semi-simple parameter lambda. So by the way, it turns out like it's supposed to study fiber by fiber. And this is roughly what happened in Dave's talk in the morning. So I take a parameter and look at like fiber and some relevant spaces, okay? And some notation, H lambda is a centralizer. And V lambda is a subspace of Lie algebra. And such that like lambda and n forms a Bayes-Drouin parameter. Well, maybe the default definition of parameter in this summit is like a radically continuous one, but like a radically continuous parameter corresponds to the Bayes-Drouin parameter, and I'm using that convention, and I'm fixing lambda, so. And fixing lambda, I consider the space of n, and such that like lambda and n form Bayes-Drouin parameters. Okay? And this is usually called, I think, Vaughan variety. And H lambda is acting on V lambda. And there are only finitely many of it. It's actually a very good space, okay? And the quotient stack I call Vaughan stack. And so we had this parameter space, and the map to the cosmoduli. And lambda determines the closed point of the cos quotient, and B lambda living over this point. So, and this is closed. This is not the entire fiber. So this is so V lambda fits in the fiber, namely Q inverse lambda. But B lambda is somehow the Frobenius simple locus of the fiber, and which is closed. Okay? Frobenius simple locus. Okay? Any other question? Okay. Now, I look at the compression along these closed substacks. Okay? And that's basically what's happening in the previous talk. I mean, it's essentially the compression along the fiber. So I look at the compression along the fiber. Well, and this may be not strictly necessary, maybe, like by, well, I guess I basically learned this from Benzoic have another, but maybe not super explicit in this way, but like this space is a unipotent loop space of the Vaughan stack. This is a unipotent loop space, and well, a mapping stack from BGA, but it's not important. No. Okay, and then I also have a compression along the smaller closed substack V lambda. And this is something called formal, because the compression along the fiber itself is a unipotent loop space. This is a further compression, and this is known as the formal loop space. So this is a unipotent loop space. And this one is a formal loop space. And by Benjamin-Adler, this space is known to be equivalent to the -1 shifted completed tangent stack. Okay. It's well, okay. I invoke some Cauchy duality, and I pass to further space. So it's at this point. Later, I guess it's not very important. I guess I really have this space here.
Sorry, what's BGA or BGU in the mapping space?
Where, sorry?
In the mapping space?
Oh, BGA. Additive, yeah. Okay. Anyway, I look at these completions. Which one? Unipotent one? It's already kind of formal. It is. No. I said like it's a closed substack of the fiber, and the Vaughan stack is a Frobenius same simple locus. Okay? And so I look at in the coherent sheaves on these completions. And there is, of course, a shrink restriction to the other completion. And I want to work something like coherent sheaf, namely, globally I have like actual honest coherent sheaves on power G, and you have a shrink restriction to these in the coherent sheaf, but it's something definitely smaller than in the coherent sheaf. And it factors through something called, I guess some people call cohat. Of these spaces. And the shrink restriction belongs to this subcategory. And I will not really define this cohat, but maybe one remark is you just think about like applying formal scheme and cohat there. And then it's actually just like coherent sheaves on the spec of A. Right? So the coherent sheaf on this like formal spectrum is more like theoretically the scheme theoretically supported on the thickening of like a modulo, say I, right? But somehow it's really allow like A itself, or well, maybe this is a Grothendieck dual to the Indo co-presentation, but like anyway. Does it make sense?
So it's some finite condition.
Yeah. Oh yeah, right. I mean, but yeah, I'm going to write that. But nice thing about this cohat is this restriction functor is equivalence. And this is known. Well, I mean, so actually, before I realized this result, I tried to prove something similar, but it turns out this is a result of alpha whole something they call coherently completeness. Okay, so somehow by working with this category, I can pass to this smaller, I don't know, smaller completion, or completion along the smaller substack. And then, so I told you this completion is kind of tangent stack. And then there is a linear Cauchy duality. Oh, okay, maybe I now consider, so for Cauchy duality, it's convenient to consider a graded sheaves. So this is a graded cohat, and grading coming from like, so this is a tangent space, so GM is acting on fibers. So using this GM action, I can talk about graded sheaves. And graded sheaves on this tangent, this is equivalent to so this is a linear Cauchy duality. Graded actual coherent sheaves on the cotangent stack.
So when you say graded coherent, do you mean coherent with an extra grading, or
Extra grading, yeah.
Okay. So just a forgetful functor.
Yeah, right. And this is actually very easy to like prove, and it's just basically restriction to the zero section, like produce such equivalence, and using like endomorphism of the like structure sheaf of the zero section. Okay. Okay, maybe I don't know. I didn't really explain, so maybe you couldn't quite follow this kind of equivalences. But anyway, the point is like it's actually enough to work with this cotangent stack, and the second talk will entirely talk about cotangent stack. But this is not the end of like the picture. So this is a cotangent stack, and it's a graded coherent sheaf. So it's a degeneration of like D module. So I can talk about D module on B lambda and filter D module on B lambda with some like coherence condition. So the second map is like taking associated graded, and you get a coherent sheaf on the cotangent stack. And the first map is just taking underlying D module. Okay? And these D module are also equivalent to the constructive sheaves on B lambda. So there are several like spaces and associated categories. And you can basically define Eisenstein series functor in each of these categories and can talk about kind of like cuspidality or like basicness of the sheaves. So so there are Eisenstein series in several settings. And also the, say, light, well, basic and right cuspidal. And somehow I restrict myself to this right version, not left. Okay? And these can be related. So somehow, using this equivalence is like, well, I first pass to this graded coherent sheaves on cotangent stack. And these functors from filter D module also like, go to the different directions, so it's not the equivalence at all. But this also helps later. Okay? Any question? All right. Okay, so we are classifying cuspidal sheaves. And the classification on this side, say this side, constructive sheaves on Vaughan stack. This is actually a very classical thing and essentially done by Lustig. So let me comment on that. So definition. Now F is a constructive sheaf on the Vaughan stack, and this is cuspidal. If the map from Eisenstein series bunches, and here so P is a parabolic, but actually, I guess there was an earlier question. This is semi-standard. I need really allow like all semi-standard, not just standard. Okay, and the lambda factors so m hat contains a fixed maximal torus. Why? Well, again, well, I mean, we want to classify cuspidal sheaves on like coherent side, but like already classification of cuspidal sheaves on D module or under equivalently the under Riemann-Hilbert correspondence, like cuspidal constructive sheaves is known. So we basically reduce the classification, in some sense, reduce the classification to this setting. And okay, and, I mean I'll state something later, but so if lambda factors m hat, then I can think of like the diagram, and you can play the usual game, like construct Eisenstein sheaves functor. Okay. So this is essentially studied by Lustig, and I guess also maybe Sorobel, I guess. but there are two caveats. So the setting is different, especially the rustic setting is different. Also, I guess if you look at his article, the definition is different. Huh? Oh, sorry. What's the correct? Oh, yeah. So the setting, his setting, is the following. So in our language, I think G is split, and lambda is unramified. And furthermore, this like Vaughan stack or Vaughan variety is determined by just co-character. So namely, there exists a co-character such that like H lambda is the centralizer of this co-character, and B lambda is a like weight n space of the algebra. And here, n is some non-zero integer. So this is just exists. And I guess some people call this as a like graded setting. Or maybe degraded setting. So Lustig basically studied the character sheaves on the graded setting. Okay? And his definitions, so his actual definition uses character sheaves. But on the whole real algebra. So the condition is like it's a restriction of the Cuspidal character sheaves on the real algebra. Or maybe he started with local system, but anyway. Yeah. But basically, Lustig proved like this definition and the Aurea definitions are equivalent. Okay.
Sorry, what's happening on like the bottom half of the screen?
So this is a Lustig setting. So this is Lustig.
Wait, from DM, can we think this is some extra data that we can always choose, or in the cases that we want to?
So Lustig's case is somewhat special, but there is a reduction to this case. So that's I was going. Yeah.
What's in the centralizing like you wrote?
GM. So maybe. I mean it's a co-character and it's centralized.
For this choice of one parameter.
Oh yeah. Okay. And in this setting, Lustig has a different definition of the Cuspidal sheaf, but this definition is essentially equivalent to the previous one, and proven by Lustig himself. I mean, at least it's implicit in there. Okay.
One more question. In this definition at the top here, there's no grading of character or whatever. It's really just all all semi-standard and all.
Yeah.
Okay.
I mean, this makes sense for any parameter, basically. Yeah. So this is
There's no like dominant or anti-dominant condition.
Right. Yeah. And okay, I guess I should make two important remarks. So the advantage of Lustig's definition is earlier he classified Cuspidal character sheaves. And so there's a very concrete and actually kind of short list of all Cuspidal character sheaves. So concrete classification. Oh, maybe I should state one theorem. And the other is like, yeah, as I said, like there's a reduction to this setting. I mean, maybe one perhaps important remark is like this H lambda is a co-character, sorry, centralizer of the co-character, so it's automatically connected. But in general, like H lambda is like far from connected. And so this reduction basically ignores some finite information, but otherwise you can reduce to this setting. Okay?
So in loose setting, lambda is still defined using lambda in the same way, but you just ask that.
Or I mean, if you like, you can ignore lambda and you can just start with co-character. And, I mean, Lustig didn't talk about parameter, right? Okay. Okay, maybe for I said it's a very concrete classification, but I guess I forgot to state one theorem. So otherwise, I guess it doesn't quite make sense. So a theorem of Lustig basically. If there exists non-zero Cuspidal sheaf, then phi, this is a Bay-Drain parameter determined by lambda, and it's in the open orbit. I told you, like V lambda has finitely many orbits, so it has an open orbit, and if you look at the parameter determined by this point of the open orbit, then in this setting, this has to be discrete, or essentially discrete.
So is there an if at the very beginning? Like if there's a non-zero Cuspidal sheaf?
Yeah, if. Right, thank you. Okay. And more.
We get a review of the hypotheses going into the theorem and the relation between F and phi, because it's not on the page.
Where does F live?
We took a break to visit the Lustig setting, but now I think we're in.
Oh, okay. I mean, right. So Lustig essentially proved this in his setting, but we can read it to his setting, and this is more general, right? So this is more general setting, and so you can start with any parameter and constructive sheaf there, and Cuspidal in the previous sense, and then the parameter is Thank you. Yeah.
It's distributed for every n in the open orbit.
Yeah.
There's one orbit.
Yeah, it's orbit.
So the subscript is constructed.
Oh, yeah. Okay. I want to finish, but yeah, and then in this case, F is clean. Namely, F is like extension in any possible way. So it's a shrink extension, intermediate extension, and star extension, any of that. And here, this is like on open orbit. So J is a map from the open orbit. Okay?
There's two continuum in the sense that the F from 1 is the F from 2,
Any other question? I guess I don't have much time, so I'll skip for example. But maybe Bertrand will tell you. Okay, so there is again, analogous notion of cuspidality on the cotangent stack. And I guess this will be certainly defined in the next talk, I guess. And you can also ignore grading. And then one result is now, so for simplicity, assume G is semi-simple. I mean, the setting is still general, but like G is now semi-simple. And suppose I have this constructible cuspidal sheaf and has a form like a extension of L rho, and rho is a representation of S phi. S phi is a centralizer of phi, this pair lambda n. Okay? And this is a finite group. And I'm looking at like simple ones, so rho is irreducible. And then there exists unique vector bundle on the Bogan stack, and it's pulled back to the cotangent along the structure map is cuspidal. And moreover, this cuspidal sheaves, say right cuspidal, I mean, it doesn't matter, but like right cuspidal sheaves, say, is semi-simple and generated by these sheaves. So we call this like cuspidal vector bundles. And in particular, if the parameter is not discrete, there does not exist like such a cuspidal vector bundle. So actually the cuspidal sheaf is automatically zero. Okay?
What's the relation between L rho and D rho?
So you can restrict to the open orbit, then you see the classifying stack of the component, I mean centralizer. Oh, yeah, I guess I should state that. And then this restricts to the L rho, I mean the sheaf corresponding to rho.
Sorry, are we talking about coherent sheaves now, or what is this intermediate extension?
This is a constructible sheaf, right? And the classified by Lustig. And then there is a like corresponding coherent sheaf on the cotangent stack. It's actually a vector bundle. And actually they generate the cuspidal sheaves on the cotangent. And actually using that, like you can prove like a cuspidal sheaf on the actual stack of parameter is also generated by corresponding sheaves. Okay. Yeah, let me add one more thing. Yeah. So furthermore, there exists a diagram. So there was a functors D module and constructible and filter D module and I guess graded coherent sheaf. And I guess F is here, and below is here, and below is a vector bundle, but you can put it a trivial grading, so to speak. So trivial grading. And given any vector bundle, you can produce any vector bundle with grading, you can produce like vector bundle, graded vector bundle on cotangent stack. And also, if you replace grading by filtration, you can also construct filter D module. And so, giving a trivial filtration, sort of, you can construct a filter D module. And then, after taking associated grading, you recovered V-low with trivial grading. But if you look at the underlying D module, you get this Cuspidal constructive sheaf or Powers sheaf. It's almost time. Okay. The final thing is some final remark. This is not the end of diagram, and there exists a lift to Hodge module. So the one in the middle further lifts to the Hodge module, and underlying filter D module is below chilled. And this is a work in progress with Bronen and Shu. And these functors are compatible with Eisenstein sheaf functor, and then this also means basically like a sort of generalized coherent Springer sheaf and the constructive setting and coherent setting maybe on cotangent, but they are related. And this kind of generalized earlier work of Benz-Bichen-Helm-Nadler. I'll stop here.